Bismillahirrahmanirrahim. Assalamu alaikum. In the previous video, we discussed about the stability of control system. We discussed two cases. The first one in which route table has no zero in the first column. In the second case, we discussed that if the first column of route table has 1 0, and now we will discuss the third case if all elements of a row are 0. So let's start our discussion. Let's take an example. This is the polynomial, that is the denominator of closed loop transfer function. We have draw the route table for this polynomial. We can see that there is 0 in this complete row. So now what we will do, we will take the auxiliary polynomial, the polynomial above of the row of 0 is called the auxiliary polynomial, and we will differentiate this auxiliary polynomial and write the coefficient of this auxiliary polynomial, differential of auxiliary, into this rows of 0. So step by step. First step, all element of row are 0. So because the term s is missing here, so all element of row are 0. We will take the auxiliary polynomial. Auxiliary polynomial in this case will be equal to s square plus 1. The third step will be differential of auxiliary polynomial with respect to s. So in this case we will get 2s derivative of auxiliary polynomial. So the coefficient of polynomial replaces the 0 row. What is the coefficient? The coefficient will be equal to 2. So we will replace this 0 with 2 here. Now we will complete our route table according to this 2. So this 0 is replaced with 2. We have solved this route table using this 1 and 2. Minus 1 over 2, 1, 1, 2, 0. So it is equal to 1. We can see that no sign change in the first column. As no sign change in the first column, so no pole in the right half plane. But due to this row of 0, the two poles of this polynomial will be in the imaginary axis. Because we have no sign change implies that system is stable, but due to the row of 0 or the auxiliary polynomial indicate that roots are on the j omega axis, which implies that our system is marginally stable. By solving this polynomial, we can also get that roots of this polynomial are plus minus j, that is marginally stable system. What is auxiliary polynomial? Like in this case, we have s square plus 2 as the auxiliary polynomial. We have a polynomial s cube plus s square plus 2s plus 2. We have divided this into two parts, an even polynomial and a separate term. By solving numerically, we can also solve that roots are marginally stable due to two imaginary roots So if we consider this even polynomial and write it here, we get that a row of 0. So when there is an even polynomial, the auxiliary polynomial is even polynomial. Even polynomial is one in which the exponents of s are even integers or 0, like s raised power 2, s raised power 4, and s raised power 0. An entire row of zeros will appear in the row table when a purely even or purely odd polynomial is a factor of the original polynomial. So here we have even polynomial. This even polynomial is called auxiliary polynomial. In Routh array, coefficients of auxiliary polynomial are those directly above the 0 row. Here we have calculated numerically, but if we make the row table for this complete polynomial, we can get that the auxiliary polynomial will be above the row of 0. Like here no term of s is missing, but when we will solve this, we get a row of 0. The above row, the row above of the 0 row will make the auxiliary polynomial s square plus 2. That is same as we have derived in this calculation. S square plus 2. So here are few properties of the even polynomial. Even polynomials only have roots that are symmetrical about the origin. This symmetry can occur under three conditions of root position, shown as A, B, and C. The roots are symmetrical and real, are shown with A. The roots are real and symmetrical. In B, the roots are symmetrical and imaginary, and the roots are quadrantal. Thus, the row of zeros tell us the existence of an even polynomial whose roots are symmetrical about the origin. Some of these roots could be on the j omega axis. On the other hand, since j omega roots are symmetrical about the origin, if we don't have a row of zeros, we cannot possibly have the j omega roots. So let's take an example to discuss all these things. Here we have polynomial. We have drawn the row table for this polynomial and we get the row of 0. The auxiliary polynomial in this case will be s square plus 2. The derivative of s square plus 2 is 2. So we will replace the 0 with the 2. So now we will complete the row table. As no sign change in the first column, that means it looked like that the system is stable, but due to this row of 0 and the even polynomial, we know that there is symmetry of roots. So two pole will be on the imaginary axis. So the system will be marginally stable, and as no sign change, so remaining one pole will be on the left half plane and no pole in the right half plane, 0 pole in the right half plane. Another example, after drawing the 1 from here, 1, this one is from here, 3, 2, and this 2 is from here, and then making route table for this terms equal to minus 1, 1, 3, 1 and 2. Similarly, minus 1 here, 1, 1, 2 and 0. Solving this, minus 2 and multiply with minus 1 equal to 2, and here we have 2 minus 3 minus 1 multiply with minus 1 equal to 1. So here we have again row of 0. The above row is the even polynomial. S square plus 2 again. So here we will get 2. Auxiliary polynomial is the row above the 0 multiplying with the coefficient S square and 2. Differentiating this auxiliary polynomial we get 2s, and the coefficient of this value term 2 will be replaced here. Again we get 2. So no sign change. Again 2 poles in the on the j omega axis due to this even polynomial, and the remaining 2 will be on the left half plane and no pole on the right half plane. Let's take fourth example. Taking the first row 1, 8 and 16. Second row will be 2, 11 and 12. Solving route table, we get row of 0 here. Auxiliary polynomial will be the above row 3s square plus 12. Differential of the auxiliary polynomial will be equal to 6s. So we will replace 0 with the 6. Again no sign change in the first column. So due to this even polynomial, we have 2 poles on the imaginary axis, and remaining 3 poles will be on the left half plane, and no pole on the right half plane. Auxiliary polynomial indicates that the roots on j omega axis. Now, fifth example. So here we have write the coefficients 1, 1. This one is here. Sorry. Let's draw it another color due to overlapping. 1, 1 and this minus 2 here. 5 will be here and 2 minus 8. So we have made 2 rows. This 4 is obtained by solving route table. Minus 1, this term minus from formula 1, 1, 5 and fourth element of this will be equal to 1. So solving we get 4 minus, and first column will be same, and here we will have 2 minus 2. For this we have minus, first column same, and we will write minus 8 and 0. So we get 4 minus 2 minus 2 minus 4 multiplied with minus gives us 4, and again minus 8. So next solving row of 0. So what will be the auxiliary polynomial? The row above this row of 0. So this 4, 4 and minus 8. How we will make the auxiliary polynomial? 4 will be multiplied with this s square. So 4s raised power 4 plus 4s cube, 4s square minus 8. We will differentiate these term, this polynomial, this auxiliary polynomial. So 16s cube plus 8s. So 16 will be replaced here and 8 will be replaced here. Now we will solve our next term, s square s raised power 1 s and 1. So this is our auxiliary polynomial. Differentiating gives us these values 16 and 8, and solving these values row table we get this. So because of the symmetry, because our main concern is lies here for the symmetry. Here we will have one sign change. So one pole in the right half plane, one pole will be on the left half plane. And due to remaining two poles will be on the j omega axis. And from here to here we have no sign change, so remaining two poles will be also on the left half plane above the auxiliary polynomial. So we can write this to this green highlighted 2 is above of the auxiliary polynomial, and the red poles are for the below of the auxiliary polynomial. So below the auxiliary polynomial we will have to consider this symmetry. One sign change in the first column, that means we have unstable system. So the important use of route table, as we have modern calculators and tools to solve for the values of the stability, or we can say that we can find the stability of the system. But if we have unknown term like k or any parameter that is unknown in the polynomial, we cannot find the range of stability from calculator. This is use of route table, that we can find the range for unknown parameter. Let's take an example. Here we have unknown parameter k. We have to find the range of stability for this polynomial. We will make the route table 1, 2 here, 4, this 2 here, and k. By solving the route table we get this. So if we want to make the system stable, we have all the first column. This is the condition, that all the first column has no sign change. So all these terms should be positive because first three terms are positive. So 6 minus 2k divided by 3 should be greater than 0. Also k should be greater than 0. So one range have telling that k should be greater than 0. For the second condition, we will solve this 6 minus 2k over 3 should be greater than 0. That means 6 minus 2k should also be greater than 0, and 6 should be greater than 2k, which means k, which implies k should be less than 3. K should be greater than 0 and k should be less than 3. That means the range of stability for k for this polynomial is the value of k should be from 0 to 3. If the value is above or below from this range, we cannot sure that the system will be marginally stable or unstable. So for this range, system will be stable. Stability range is from 0 to 3. For what value of k the system will be marginally stable? If we have all the any row equal to 0, so this term equal to 0 and finding the value of k. So again k comes to be 3. So if we have k exactly equal to 3, the system will be marginally stable. In the second example, determine the range of k for the system to be stable. So first of all, our first step will be to calculate the characteristic polynomial. Characteristic equation is the denominator of the closed loop system, feedback system. We construct the Routh array. For the system to be stable, we must have the following two conditions simultaneously. First, k should be greater than 0, and second, 6 minus k over 3 should also be greater than 0, which implies 6 minus k should be greater than 0 or k should be less than 6. So range of stability is from value of k from 0 to 6. For k exactly equal to 0, the characteristic equation becomes equal to 0, and then solving we get that the pole is at origin. That means the system is marginally stable for k equal to 0. For k exactly equal to 6, the characteristic equation becomes making factors. We get s equal to minus 3 and two imaginary x's. The system is marginally stable. So at k equal to 0 or k equal to 6, the system is marginally stable, and from 0 to 6 between these values, the system will be stable. And the frequency of the oscillation will be square root of 2 radian per second due to this. Third example, again putting these values in the Routh table. So 4 minus k over 2 should be greater than 0 in order to system stable. That means 4 should be greater than k over 2, or k should be less than 8. So next condition is k minus 12 over 4 minus k over 2 should also be greater than 0. If we find the value of k from here, we get a complex root, but it should be greater than 0. Here we have complex root. That means the system stability range cannot be satisfied for any value of k due to these complex roots. So polynomial has right half plane roots for all value of k. Let's suppose we have value of k equal to 2. So let's take the value of k equal to 2. For example, here we have 2. So we get 3 here, less than 8, the condition is satisfied. But here we will have 2 and again 2, 1, 3. So 2 minus 12 over 3, which is equal to 2 minus 4 and minus 2. So pose are in the right half plane. By taking any value of k, the system will be unstable. So Routh table can also give us the range of stability for any unknown parameter. So here we conclude our today's lecture. Thank you very much. Allah Hafiz.